Our next two examples are related, so I'm going to do them both at the same time so we can do a comparison. In the first one we have a non-conducting slab, so it's a flat surface, so the charges aren't going to move. So we know we have an electric field coming out of the surface on both sides. Because the charge is uniform, then I know that the electric field is coming straight out. There's no fields inside that are horizontal. So I define my charge density, sigma, is equal to the amount of charge divided by the area. And now I want to solve for Q, and that's just equal to sigma times A. So let's draw a Gaussian shell, and that shell is going to be a cylinder where the cylinder circular part extends through the slab. And you see it's open on the backside. So the cylinder extends all the way through the slab. And this is our value A that we're looking at for our charge density. And now we can apply Gauss's law. My E is constant, magnitude, differential area, and my Q enclosed is just going to be sigma times A over epsilon naught. And my area, when I do the integral, well, there's no horizontal electric field, so the circular part has no contribution. I'm just going to have the end caps, and I'm going to write that as 2 times the area, A being the area of the end cap, and that's equal to sigma A over epsilon naught, and that just means the electric field is equal to sigma A over 2A epsilon naught, and that's just equal to sigma over 2 epsilon naught. So this is for a non-conducting slab. Let's look at the instance of a conducting surface. Have the charge along the edge here. I'm going to draw a sphere, or I'm sorry, a cylinder, very similar. I'm going to draw it really tiny because this is actually a non-flat surface. So I'm going to draw a tiny cylinder. And I know that if this is a conductor that the electric charge is distributed on, my electric field is only in the direction away from the conductor. There's no electric field on the backside. So again, my surface charge density is equal to Q divided by AS. And I'm putting this S in here because I want to differentiate it from the previous problem. So again, I have integral electric field dot differential area equal to Q enclosed over epsilon naught. The E is going to come out, And now, here again, I'm going to solve for Q in this formula for the surface charge density, and that's just going to be sigma times AS over epsilon naught. And in this case, because the electric field is not coming out of the back end, it's only coming out through the top, and that area is, we'll say, A, then I will have electric field is equal to, electric field times A is equal to sigma S times AS divided by epsilon naught. So E is equal to, well, if I divide, actually this should be AS. If I divide by AS, the AS's are going to go away, and I get sigma S over epsilon naught. So in this case, it's interesting because you get something similar, but in the case of the non-conducting slab, the electric field strength is half of what it would be for a conducting slab. And that's because the electric field gets split along the front and back side of the non-conducting shell versus it's all in one direction for the conducting shell.